In this segment, we'll take a closer look at quantum mechanical operators in Dirac notation, and that they will be introduced and related to the so-called outer product of the state vectors. And we'll take a look at it. Let's review a little bit to sort of put this in context. And remember, we've introduced the inner product of a ket and a bra vector as follows. If it's finite dimensional, and that's what I want to look at here, then the inner product of a ket vector A and a bra vector B is this bracket symbol. And if they're finite dimensional, it's just the sum over all the individual components of psi star B times the corresponding component of A. And then just to illustrate that, for finite dimensions, if I have A is, we're representing ket vectors by column vectors. And B, remember, is a bra vector, and it's the Hermitian conjugate of a ket. And the Hermitian conjugate, this dagger operator, is well, the way I usually do it is I first take all the complex, I take all of the components of it, I take the complex conjugate of it, and then I transpose the whole matrix. So in this case, the dagger operator, the first thing I would do is I would complex conjugate B1, B2, B3, and then I would transpose it. And a transpose of a column matrix is nothing more than a row vector. So I have a column vector and a row vector. And now then, this product is really just regular vector multiplication. It's really just a regular dot product. It's the sum of B1 star times A1 plus B2 star times A2 plus B3 star times A3. And I think that's written down below it. And remember, when we've got complex numbers for these A's and B's of i's, that this thing in general is a complex number. Yeah? So the inner product takes two state vectors, a bra and a ket form, and with those combines those in a way to get a single scalar quantity that is a complex number in general. And so sometimes this inner product is also called, because of that process, is a scalar product, much like in the case of vectors. Yeah. Remember, we had this relationship that I think we actually demonstrated that in some degree of generality. But if I interchange the order of A and B, then they're related, but by a complex conjugate. The inner product of A and B is the complex, or the inner product of B and A is the complex conjugate of the inner product of A and B. For infinite dimensions, the situation is virtually identical. It just looks a little bit different. Okay? So here I've got a state function. I actually gave it a parameter, t, which oftentimes they are. So you can think of this as a state of a quantum system at time t up here, state of the quantum system at time t here. And we made the identification that this, what we'd been calling the wave function, psi of x and t, we're just looking at one dimension here, the x really is a continuous label. So x is like the I up here in this previous expression up here. It's just the sum over all the components. But now I've got a continuous number of components labeled by x. And so if I want to define the inner product, I'm going to have to take a continuous sum over all of these all of the x's. And so for infinite dimensional Hilbert spaces that a lot of the quantum mechanical systems are described by, if I took the inner product of these two state vectors, I would get the bra form for this one, the kit form for this one, and then I simply really kind of think of this as a definition. It's the sum over all the components of the first one complex conjugated and the second one as it is. Yeah? So notice the summation over I for the discrete case is really turned into this integral. Well, that's again a synopsis really of a lot of the things that we've done previously. But now let's look at introduce something that we're going to call an outer product of the kit vector B and the bra vector A. And for right now, I'm just going to define this symbol. Whether it has any meaning or not, we'll have to see. But I put them in different order here. Is the kit outer product, I write the kit on the right and the corresponding bra on the B on the left. And whether or not that means anything, we have to interpret. Okay? So what does it even mean to write that? Okay? And to examine that, let's take a look at applying this thing that we just defined, that outer product of these two vectors, to a different state, another state, C. And so I simply have my, whatever this is, that is being applied to this state C. And I think that has a pretty natural interpretation, as this one's B stays the same. And here I've got A, B, and that just becomes the inner product between those two. AC, I should say. AC just becomes the inner product. And again, this is simply a complex number. To make it explicit, I can write it out here as lambda, where that's a complex number. That's the inner product of A and C that we've just gone over. And a number can go on either side. In fact, it can come inside, as we've seen here. But this lambda B is simply another state, which I call it C prime. Lambda B is C prime. Okay? And so what we found is this. We found that by operating with this thing, this outer product, onto a vector, it simply produces another state vector, C prime. So it produces a mapping or an operation. And that's exactly the way we defined operators. Symbolically, we're starting with C. We apply to it this thing, this entity, the outer product. And what it does is it transforms C into C prime. So, and again, that's exactly what an operator, what we defined the operators to do. And so oftentimes they'll take these and then assign them some letter, you know. Here I did G, but I could have used M, you know, B, the capital B. Usually operators we denote by capital letters. For finite dimensions, we can get a little more meaning from it and see precisely what this outer product is. So this could just be a regular vector space with regular vectors. And I want to get the outer product, BA, up here in this form. And so for that, I'm going to need the two vectors. Remember, a kit vector is, for us, is a column representation, column vector. And a bra vector is a row vector, okay? And so this form here, I have to keep the order important because it all becomes matrix multiplication, and order is important for matrices. And so this A becomes the row, and this B here becomes the column. And now then you just use the usual rules of matrix multiplication to multiply these. The thing that's a little bit different is it's really simpler to do. The way you multiply these two together is the following. You multiply this element times every element in this row, and that first element becomes the first row. B2 times all of these, A1 successively, A1, A2 becomes the second row, And B3 times the A1, A2, A3 multiplied by each one is the third row. So you have the three rows. The first row is this element, the first element times the vector. Back again, the second row is this one times it, and the third is this treating it as a scalar times this vector and writing its components this way. Now you might lump these together and write these in pretty distinct order, really, as BIAJ for the components of this operator. So it's represented as a linear operator, as a matrix. And remember, the first index, whatever's here, it designates the row, and the second index designates the column. And so if I'm over here in this element at this point, this is in the third row in the second column, so that's B3, A2, and that would be this element here. Well, again, I'll note that in general, these two different outer products, the outer product of A and B, is not the same as the outer product of B and A. If I interchange if I switch this B to an A and this A to a B, I get this. And in general, those are not equal. In fact, most of the time they're not equal. And the reason is pretty much the same as for matrices. This quantity here becomes BIAJ, and that becomes MIJ. So that's this side. But if I have the alternate, the first index, it would be still have A's and B's, but it would be AI BJ, and those two are not in general equal. Right? So MIJ is not equal to MJI because those two pieces in general are not, for a specific I and J, are generally not the same. This would be B2. For instance, if I was looking at the 3-2, I think is what we looked at, 3-2. So if this is J is 3 and A is and I is 2, so B3 times A2. But over here, J is 3 and B is J is 3 and B is 2. And over here, BJ is 3 and A is 2. So in general matrices, you cannot interchange rows and columns, and that is reflected in this inner product.